Great. Let's start this conversation. So first up, we have Lukas Barth from the Max Planck Institute, who's going to tell us something about metric spaces and fuzzy simplicial sets.
Hey everybody, I'm very happy to be here. So first of all, let me say that this is kind of joint work with those amazing collaborators. They've all contributed to different aspects of what I'm going to present. Unfortunately, they cannot be here right now, but I hope at some point they can introduce you to them. So we have a couple of sections ahead. First of all, I want to give you a little introduction what this is about. So our fundamental question is how to apply category theory to manifold learning and data visualization. And what does that even mean? So manifold learning usually is about having a finite data set, usually it's embedded in Rn, and one wants to kind of extract a lower dimensional representation of it. Usually one does that by generating embeddings in Rd, where the dimension d is much lower than n. And those Rd embeddings, they can be thought a little bit as charts of the manifold. So you can imagine you have maybe a 1,000-dimensional space, and in this 1,000-dimensional space, the data is distributed or concentrated around some manifold that hopefully has much lower dimension. And we kind of want to find that or want to find charts of this manifold. And those embeddings serve a couple of purposes. So first of all, they can increase the computational efficiency of downstream tasks. For instance, you could first embed all the dimension in a lower dimensional space and then train a neural network on the embedding instead of the actual data. And if the embedding does not distort the data too much, this can increase the efficiency very much. Or it can help you to interpolate the data. And if you choose the embedding output dimension to be 3 or 2, you can even use it for a visualization. To give you a couple of examples here, those are like toy examples. Here we have, for instance, a torus in 3 dimensions, and then there are 3 common methods. One of them is just linear projections to kind of looking for the best linear projection that preserves things as good as possible. Works kind of well for this torus, but you see already for this Swiss roll with a hole that you have problems resolving the actual geometry. And this isomap here, for instance, manages to unroll this hole. So you this Swiss roll, and you see this kind of is much more like the intrinsic geometry of the actual manifold. But then it usually has problems to do this for higher dimensions. So here you have, for instance, this MNIST data set with the handwritten digits, and you see that here the clusters cannot be easily resolved. Well, this UMAP method has the disadvantage that it distorts the low-dimensional manifolds more, but then it can usually separate the clusters much better. And we were kind of inspired by this idea of UMAP, and because it has to do a lot of things with category theory. And so I want to show you what exactly and how one could possibly expand on that. So to do this, I give you some preliminaries. So first of all, just introduce those metric spaces so that we're all on the same page. I mean, we have Uber metric spaces that are kind of like pseudo-metric spaces where you also allow infinite distances. And apart from that, they fulfill the usual metric relations. And the category of those Uber metric spaces we call UM, and they have non-expansive maps, which means that kind of dy of f of xx slash is lower or equal than, so it kind of doesn't increase the distances, the morphisms. And one kind of fundamental operation that one can do is one can consider a splitting of this metric space into n nearest neighborhood spaces. So you declare kind of for each point, you declare a new metric space which has the same underlying set, but where the distances only to the k nearest neighbors are finite and all the others are set to infinity. And this is supposed to be helpful to compute the intrinsic geometry. For example, if you look at this spiral, intuitively we want the red dots to be further away from the blue ones than from the yellow ones. But if we take the Euclidean distance, they're actually closer. So in order to prevent that, we take just distances on k nearest neighborhoods and then just walk our way along those k nearest neighborhoods until we reach the red dots to get the kind of intrinsic geometry of the manifold. So that's why we want to have this splitting operation. And the idea is then that those finite distances in those neighborhoods, since they are all small, the Euclidean distances are still like close to the actual distances on the manifold, and we somehow have to patch them together. And the question is, how do we combine those neighborhoods? And in order to do that, we have to use a combinatoric representation, and this is where the simplicial sets come in, because they are a convenient combinatoric representation for this metric data. So what are those fuzzy simplicial sets? So those were first defined by David Spivak. And yes, we start with a fuzzy set, which is not yet simplicial. It's just a sheaf on this poset category 01, where all the restriction maps are injections. And if you have a little bit of a difficulty to parse this intuitively, you can just think of a classical fuzzy set, because this is actually, they're like the categories are isomorphic. And that is just a pair where X is a simple set and ether is a simple function to the interval. And the functions are increasing in in opposition to the metric morphisms. They are kind of expansive. And those are isomorphic, so intuitively we can always just think of those classical ones, and then we combine this with simplicial sets in the following way. So we have this simplicial indexing category that you're probably all familiar with, where you just have those totally ordered sets as objects, and the morphisms are just order-preserving maps. And then we define simplicial sets usually as functors from delta OP to set, and a fuzzy simplicial set is simply a functor from delta OP to fuzz. And the morphisms are the natural transformations. And intuitively, you can really think of a fuzzy simplicial set to be a simplicial set where every simplex additionally has a strength, and it fulfills a compatibility condition, which is that the strength of the simplex is lower or equal than the minimum of the strengths of the faces. So that's kind of what those fuzzy simplicial sets are. And in contrast to the simplicial sets, you additionally have those weights, and they are real numbers, so they can quantify metric information. So that's why we are kind of moving from the realm of topology to geometry. And Spivak showed that there is an adjunction between the fuzzy simplicial sets and the Hilbert metric spaces, and that's why they are related. So Spivak defined this generalization of the usual geometric realization of a topological space by saying, okay, we just this is just on the kind of category of representables, in the subcategory of representables, you can define this metric realization, and instead of setting this equal to be 1, which would give you a normal geometric realization of a simplex, you set it equal to minus log A, which then gives you kind of simplices of different sizes when you're geometrically realizing them. And then you can use Kahn extensions to kind of show that this actually can be extended to the functor from S-fuzz to UM by taking the co-limit of those representables. And here you basically have simplices of different sizes that you're realizing, and you fill also the faces of these simplices, geometrically speaking. And in UMAP, the authors defined a different adjunction from finite fuzzy simplicial sets to finite metric spaces, where basically on the representables, this just acts by realizing n+1 points where the metric is constant. So it's like the skeleton, it's like the skeleton functor of this functor here, where the faces are not filled anymore. And those two adjunctions, they are actually both, they can be viewed as being kind of children of the same theorem, so to say. So like one small contribution is that one can show that one can use this nerve realization theorem to actually say, okay, we can consider this more generally. We can say that if C is any category that has small colimits, then the following actually defines the functor. So you just have to define any functor Re delta. This can be the one of Spivak, or it can also be the one of the UMAP authors if you consider this finite fuzzy simplicial set as a subcategory of S-fuzz. And then C just has to have small colimits, and then you always have this this functor, and you always have a right adjoint, which can be shown to have this form. So it's just like the home sets from those geometric realizations to the space we're mapping into. And the nice thing about this right adjoint is that it's actually like a rescaled Viator-Serbs complex that you know from topological data analysis. So you kind of look at your space, and while you're increasing this value A here, you're actually, while you're decreasing this value A, you actually capture more and more and more of the kind of vertices in your metric space. So these are the points in your metric space, and you put them into the cliques of what's becoming your simplicial complex. And so here you have this nice relationship, and UM and EPMet, they both have small colimits, and so you actually can show that this is all well defined. In the case of finite EPMet, they actually don't have small colimits because you could have infinitely many, like an infinite product, so this wouldn't actually hold. But perhaps one can still show that this colimit exists if you restrict yourself to this finite for the simplicial sets. In any case, this is kind of the general setting how they are related. But in general, this colimit might be difficult to compute. And in fact, in UMAP, they are not really using this colimit or the realization functor. They only use the sync functor in order to obtain the dimension reduction algorithm in the following way. So we can go through this UMAP pipeline diagrammatically. And we start with this metric space, then we split it, as I explained, in those local neighborhoods. And afterwards, we convert this into fuzzy simplicial sets, into n fuzzy simplicial sets by taking this Virtuous Rips filtration and the cliques out of it. And we get this combinatoric representation. And then what's done in the UMAP paper is actually that they only keep the underlying directed graph from this. So they truncate this. So the CTR is the truncation. And then they merge it with a certain merge operation on which I will expand on the next slide, to get one single directed graph. And then they embed this using some minimization procedure where you minimize the so-called fuzzy cross entropy, which is what is here in equation 6. And if you know, then this is probably clear to you. If you don't, let me just tell you two properties of this equation 6. So if this is always bigger or equal to 0, and it's 0 if and only if Hij is Gij. So by minimizing this, you try to make Hij similar to Gij, where Gij is this high-dimensional directed, or this directed graph coming from the high-dimensional data. And this Hij is a graph that is obtained in a similar way from low-dimensional data. So you have points in, for example, 2- or 3-dimensional Euclidean space. We go through a similar procedure to obtain, again, fuzzy simplicial complex, and then you minimize this cross entropy of them. And in this way, you obtain an embedding where the result is some lower-dimensional set of points that has the same cardinality as the set of points you started with. So this is like the general procedure. And one thing you might notice that this realization functor is actually not used in the process. So we were asking ourselves if one could instead go along this alternative path. So we start with these splitted metric spaces, and we directly compute this composition of functors here of this sing, merge, and RE functor. And in order for this, we had to compute what this realization functor actually is, how to compute this colimit, and we had to generalize this merge procedure, which is here only performed on directed graphs, to the general simplicial case. And so this is what I want to show you next. So first I go into metric realizations. So we compute the colimit of the diagram in Huber metric spaces. And maybe this was done before, but we didn't find it, so we did it ourselves. And it turns out that this colimit is a very natural object. So it's just given by the colimit in the underlying category of sets, together with a metric that is described by this infimum here over all possible paths that go through those equivalence classes where the points are being glued together. So you have those P1 and Q1. They always have to be related by the fact that Pi plus 1 is in the same equivalence class as Qi. P1 is in the equivalence class of X, and the last point is in the equivalence class of X slash. And so what you can think of this intuitively, so maybe when it looks a little bit unwieldy if you didn't encounter it before, but it's really a very natural operation. So as an example, consider simply a straight line. Like for instance, the interval with the Euclidean metric, and then you identify the two endpoints to get something like a circle. Then this infimum is really saying, okay, you can start at any point in the line, you can walk to the final point, And then because of this, you are allowed to jump to the first point to go on measuring the distance to any other point. So this is really a very natural object that comes out. And in fact, it is something that people that were working in metric topology were writing down before, as we discovered later, without knowing about this adjunction and so on. So it shows once more, so to say, that categorical nonsense can give you kind of meaningful results. And we are very happy about this coelement result. And using this, we can now compute the realization functor, which was defined in terms of this colimit. So maybe I go briefly back. You remember that we had this colimit. The realization factor is just the colimit of this composition. And so we can compute this now. And what we get is indeed, again, this infimum distance, basically. And we show that at least for the junction that was defined in UMAP, this thing factors through the directed graph. So you don't really get more information from the upper cliques, which is also kind of natural because the information in the Vietoris-Rips complex is basically determined by the underlying directed graph. And this is reflected here in the realization functor, where again, you have this infimum distance, but now this d min here is basically coming from the weights on your graph. So you have this fuzzy simplicial complex. S1 is the underlying graphs with some weights. And some of those weights, they are with some edges, and some of those edges carry this weight log psi1 of S. And then intuitively, you can really say that our U generates a metric space in which the distances are the geodesic graph hopping distances along the edges of the underlying directed graph. And this is really, when you go back to this picture of the spiral, what we wanted. So we start with those local neighborhoods, and then the realization functor after the splitting, when you bring them together again, you really get this geodesic graph hopping distance. So it's really nice that this all comes out purely from categories theoretical arguments. And so in order to compute this alternative path, the only thing that is missing now is merge. So we know this is the Vietoris-Rips filtration, this is this natural geometric operation, and we only need to define merge. So we'll show you how to do this in the next slide. We start with something that's called a T-conorm, which is like a probabilistic operation, which is simply something that takes two real numbers as input and spits out a real number, so two probabilities, and gives you back the probability. So it's a very simple thing, and it fulfills certain axioms like symmetry and others that are related to the metric axioms, or that are similar to the metric axioms, but they are motivated by probability theory. And then we can lift this to the category of fuzzy sets or classical fuzzy sets by saying, okay, we define a functor on this pullback category. So, this is the pullback of classical fuzzy sets over the category of sets, the pullback in the category of categories. And we define this by saying, okay, we define the merge of two classical fuzzy sets that have the same underlying set simply by applying the T-conorm, so to say, on those edges, so edgewise. And then, so this is also inspired by what the people in UMAP were doing. And now we are going on to lift this further to the category of fuzzy simplicial sets. So first, this gives us a merge function through the isomorphism from fuzz to C-fuzz. And then here on fuzzy simplicial sets, we can just, again, define this, so to say, for every n, we just reuse our operation that we defined here. And then one has to prove that this is well defined because one still has to show that this fulfills the compatibility condition on the simplicial complexes. And this can be done. And so in this comparatively straightforward way, you can lift this very simple operation to fuzzy simplicial sets. And then we can combine everything and achieve our aim to actually compute this merge UM as this composition of those three functors. And what comes out is, again, this infimum distance here, but instead of this minimum that you saw before, we now get minus log, which is, again, converting the probabilities into actual metric distances of TR, which is a recursive function that kind of recursively applies the T-conorm to all the different possible edges that are supposed to be merged there. And in this way, we kind of compute this alternative pathway. And this suggests an alternative algorithm because now we have this merged metric space where we have the geodesic distances on the manifold. And the only thing that remains to do is to embed it into some Euclidean space. And there are different embedding methods. One could use spectral methods, or one could use multidimensional scaling, or one could use metric multidimensional scaling. So in the end, we decided for metric multidimensional scaling because it's kind of the nonlinear method that can capture more differences. And so a concise description of our method is that as input, we have just some data set that is finite, and we split this. And then in this, to obtain this n metric spaces, in the second step, we apply this merge functor that we defined on the last slide. And then we have to compute the co-limit, which is kind of computationally more costly because it involves this infimum. But this infimum can be computed using Dijkstra's algorithm. And because our graph is very sparse, because it's a k-neighborhood graph, this is not too costly, and one can also parallelize it. So we implemented the parallel version. And then we embed the result of that using metric multidimensional scaling, which again minimizes sort of the distances, minimizes the distance between the two distances in the low and the high dimensional space. And this is similar to UMAP. Because we also proved, which I didn't show here, that REU after Sing is the identity, which means that UM is a fully faithful subcategory of SFAS. So you can completely represent all the information of any metric space in a fuzzy simplicial set. And this means that fuzzy simplicial sets are kind of a good setting for doing metric geometry, or even generalized metric geometry, because you can encode any metric in it, but at the same time, you can also encode non-binary relationships. For instance, if you have social networks or something where you need more relationships, then you can use this fuzzy simplicial sets. And you can be sure that you don't lose any information along the way. And then after applying Sing, which is like fully faithful, then we merge and then we map back. We can be sure that kind of we actually don't lose information along the way. And that's why we have something that is very similar to UMAP in that sense. But at the same time, it can also yield this dimension reduction algorithm isomap if we choose a comparatively simple embedding method, classical MDS, and if we choose our local metrics to be comparatively simple and our T-conorm to be simple. So by setting certain parameters to simple values, you also get isomap, and then we have like a very nice mixture and a bit of an unexpected relationship between those two well-known methods. And that's why we call it ISUMAP, because it also takes place in the category UM. And so let me show you finally some examples. So we implemented this algorithm. Here we have the input data. UMAP kind of distorts the low-dimensional representation. ISOMAP doesn't do that, but ISOMAP also isn't capable of uniformizing the data distribution. So here you see these data points here are more dense in the center and less dense here. And UMAP and ISUMAP, they managed to kind of expand this green region. You see this here very clearly, which uniformizes the data distribution, which can be useful for certain applications. And ISOMAP doesn't really do that. So we have less distortion than UMAP while retaining similar capabilities for those low-dimensional data sets. For high-dimensional data sets, UMAP still obtains a better clustering, while our clusters are, from my point of view, somewhat clearer than those of ISO. So this is ISUMAP, this is our method, kind of slightly more clearly separates the clusters than in ISOMAP, but doesn't separate them as clearly as UMAP. But on the other hand, UMAP has the danger to separate things that are actually not that far away. So for instance, here we have the breast cancer data set, and the red points are malignant cancer cells, and the blue ones are benign ones. And you see that, for instance, UMAP puts some of the benign cancer cells also together with the malignant ones, and this can be sort of dangerous for the interpretation of the result, while our method, even so, it kind of yields better result than ISOMAP, shows you that it's actually not that clearly separable. So we have sort of less distortion, and I think this can be useful for some applications at least. Well, this is sort of my last slide, just as an outlook. One could combine our method with functorial manifold learning and functorial clustering as introduced by Dan Schiefler. So this is kind of to equip our method with a better clustering capability. And we are already working on this and have some preliminary results, which I however, omitted from this talk. That's one possible direction. Another one is that one might ask, okay, how does UMAP actually achieve this distortion? Is this all because of this this loss here, of number 6, because only the embedding was different from our method, right? And actually the answer is no, it's not just because of equation 6, it's also because UMAP actually uses a negative undersampling here. So it undersamples the second part here, and this has a very strong effect, which was pointed out by Damrich and Humprecht. And so this is not completely understood. And to understand completely this effect, one would have to go into the gradient descent stochastic procedure itself. And maybe to formalize that from a categorical perspective, one could use things as spectrum as a functor or learner's language or categorical system theory. So one could use kind of interesting things of people that are also here at this conference to try to understand this last step of the distortion better, because it's not really well formalized. And finally, there's a connection to topological data analysis, because we have this connection to the virtuous filtration, but we can also capture geometric information. So I think that this theory actually has interesting relationships to a couple of other fields. And that's basically it. So if you're interested, please read our preprint, which you can find there, fuzzy simplicial sets and their application to geometric data analysis. And our code is also open source. And you can contact me anytime for any constructive or destructive feedback. We're happy for any interest. So yeah, thank you very much.
Thank you. We started a little bit over time, so we have a few minutes for questions. Are there any?
Yeah, like y delta times I. Well, I didn't understand what that was.
All right. Yes. So you apply the Joharinad embedding. It's like the this one here.
Yeah.
Yeah, so delta is the simplex category, I is the poset category. And then you basically, this is the image under the Joharinad embedding of this category. So it's a subcategory of SFAS. Because, okay, maybe that's not entirely clear. So SFAS was defined as a functor from delta OP to FAS, but you can do a currying operation, and then it's a functor from delta times IOP to sets. And that's why the Joharinad embedding gives you a subcategory of the simplicial sets. That's basically the reason why Spielberg introduced this sheaf formulation, because then everything actually has codomain sets and becomes really nice, and you can show this adjunction with the standard methods that you already know.
Thank you.
Any other questions? Oh, let's thank the speaker again.